Hello everyone, welcome back to the channel. So in the previous session, we have discussed about lanthanide contraction, cause for a lanthanide contraction and effect of lanthanide contraction. Okay, that is consequences of a lanthanide contraction. Yes, now in this session, we are going to move on the next concept of the chapter, that is general characteristics. General characteristics of and uses of lanthanides, general characteristics as well as uses of a lanthanides. First we consider the general characteristics of a lanthanides. Okay, yes, the first characteristic is all the lanthanides are, if you consider how they appear. Okay, all the lanthanides, their compounds are silvery white. If you consider lanthanide elements, all the lanthanides are silvery white soft metals. Okay, they are, what is the nature? If you consider physical state, they are silvery white soft metals and tarnish rapidly in air because of their reactivity. Okay, because of their highly reactive nature, what happens? Their surface readily tarnishes rapidly. Tarnishing is nothing but it readily combines with oxygen content and get converted into its oxide, LXOY. A oxide layer will be formed on their surface. Okay, yes, what is the first general characteristic? All the lanthanides are silvery white soft metals and tarnish rapidly in air. Their surface readily tarnishes in the air. Okay, well, second one, regarding hardness. The hardness increases with increasing atomic number. So from lanthanum to lutetium, what happens to the hardness? Hardness increases. Okay, hardness goes on, increases with increase in the atomic number, which means if I consider which is soft, lanthanum is most soft among lanthanides and lutetium is hard. Okay, among all lanthanides, that is hardness increases with increase in the atomic number. Okay, well, is the second characteristics. First one, they are silvery white soft metals, their surface tarnishes readily in presence of air. And third thing, if you consider, the hardness of these metals increases with increasing the atomic number. Okay, well, next one, many trivalent lanthanides. Okay, many trivalent lanthanides means Ln3+. Generally many trivalent lanthanide ions are colored. They are going to exhibit a color. I already mentioned why they are going to show color, means it is because of what? F transition. So yes, if you consider in their trivalent state, many trivalent lanthanide ions are colored one. Okay, they are going to exhibit a color both in solid state as well as in aqueous solution. Means even in its solid state as well as in aqueous solution, these trivalent lanthanide ions are going to exhibit a color. And further, that color of these ions may be attributed to the presence of F electron. As I said, the color, there must be a unpaired, I said no condition to exhibit color, there must be an unpaired electron. Second thing, there must be vacant F orbital at a higher energy level. Okay, and there involves a F transition. So it is a criteria to exhibit color. So the color of these ions may be attributed to the presence of an F electron. If there is an electron in the F subshell and it is unpaired electron, and if there are vacant F orbitals are available at higher energy level, so there involves a FF transition and that compound or that species is going to exhibit a color. Okay, yes, what is the third characteristics? It is a many trivalent lanthanides, they are going to colored both in solid state as well as in aqueous solution, and that color may be attributed to the presence of what? Presence of an F electron. Okay, well, now coming to the next one, next general characteristics. Neither lanthanum 3+ nor lutetium 3+ ions show any color. If we consider lanthanum 3 plus, lanthanum 3 plus means 4f0, 5d0, 6s0, outer electronic configuration. Similarly, if you consider the last element, lutetium 3 plus, what it is, 4f14, 5d0, 6s0. So here, why we are saying neither lanthanum 3 plus, lutetium 3 plus ions show any color means, yes, in case of lanthanum 3 plus, there is no F electron. There is no F electron. And what about lutetium 3 plus? There is no unpaired electron. There is no unpaired electron. There is no vacant orbital. So lutetium 3 plus also colorless, and lanthanum 3 plus is also colorless. Therefore, we are specifying neither lanthanum 3 plus nor lutetium 3 plus ions show any color. But what about rest of the ions? Yes, rest of the ions do so. They are going to exhibit a color. However, that absorption bands are narrow, probably because of excitation within the F subshell. Whatever the absorption band we observe, it is very narrow. Okay, we are going to observe a narrow range of spectrum. It is because what? It is because of excitation of the electron within the F subshell. Okay, yes, is the next characteristics. Then most of the lanthanide ions are paramagnetic. We know paramagnetic properties because of what? Because of presence of unpaired electron. How the paramagnetism is due to presence of a unpaired electron. Okay, yes, most of the lanthanide ions, they are going to have unpaired electron, one or more unpaired electron. Therefore, they exhibit paramagnetism. What is the exception? Except F0 configuration. F0 means what? There is no electron at all, right? There is no unpaired electron, then there is no case of paramagnetism. F0 example, lanthanum 3 plus I can consider, say F0. Cerium 4 plus, yes, it is also F0, there is no electron. And F14 type. F14 means, say, if all the electrons are paired, then there is no case of paramagnetism. So remember, paramagnetism is a characteristic of what? It is a characteristic of unpaired electrons. It's the property which is exhibited by what? Unpaired electrons. In F14 configuration, there is no unpaired electron. Then there is no question of paramagnetism. Okay? Yes. So most of the lanthanide ions are paramagnetic except what? Except F0 and F14 configuration. F0 example, lanthanum 3 plus I can consider, cerium 4 plus. These are the well-known examples. Then if I consider the F14 type of, okay, F14, lutetium 3 plus we already considered, lutetium 3 plus, and along with ytterbium 2 plus is also example. So in these cases, they are going to have F14 configuration and there is no unpaired electron, therefore they do not exhibit paramagnetism. Well, if we consider the series, for F series, that paramagnetism rises maximum in neodymium. Okay, so if you consider lanthanum, cerium, praseodymium, neodymium, so paramagnetism rises maximum in neodymium. Well, then if we consider chemical reactions, okay, so lanthanides in general, they react with different chemical species and gives various type of compounds, corresponding compounds. Well, say consider lanthanides when react with halogens. Yes, they gives respective trihalides. Really, lanthanides when react with halogen, they give respective trihalides. LnX3 lanthanide trihalides will be formed. Similarly, lanthanides react with water, means they undergo hydrolysis to give respective hydroxides and liberate dihydrogen. Okay. So the one reaction is lanthanides react with halogen to give respective halides. Respective halides will be formed, and lanthanides readily undergo hydrolysis, means lanthanides readily react with water to give respective hydroxides with the liberation of dihydrogen. Dihydrogen is liberated during that reaction. Then further, if you consider when lanthanides are heated with coke, okay, lanthanides when heated with coke at around what is the temperature, 2773 Kelvin temperature. Lanthanides when burnt with coke, or I can say carbon, at 2773 Kelvin temperature gives respective carbides. Okay, respective lanthanide carbides are formed. Is the third reactions exhibited by lanthanides. So first, they react with halogens to give respective halides. Lanthanides readily undergo hydrolysis to give hydroxides and liberates dihydrogen. Lanthanides when burnt with coke at 2773 Kelvin temperature gives corresponding carbides. Okay, well, next, say lanthanides when heated with nitrogen gives corresponding nitrides. Lanthanide nitrate sulfide, nitrates are formed. Okay, then they show reactivity with one nitrogen, right? So is the fourth type of reaction. Then when they reacted with sulfur, lanthanides when heated with sulfur gives corresponding sulfides. Okay, corresponding sulfides will be formed. Ln2S3 lanthanide sulfides are formed. Then lanthanides when bonds in oxygen, when they react with, or you can say combustion, when lanthanides are subjected for combustion, the corresponding oxides are formed. Oxides, that is Ln2O3, general formula. Ln2O3 is the lanthanum oxides. Okay, well, then lanthanides when react with acids they liberate dihydrogen. So means if you consider reactions, chemical reactions exhibited by lanthanides is generally they show reactivity towards halogen, gives halides. They show reactivity towards water, means on hydrolysis gives hydroxides. They even react with the coke at 2773 Kelvin temperature gives carbides. They show reactivity towards nitrogen to give nitrides. Okay, they show reactivity towards sulfur to give sulfides. They show reactivity towards oxygen, that is they undergo combustion to give corresponding what? Corresponding oxides. Then they even show the reactivity towards acids and liberates dihydrogen. Means yes, lanthanides also a reactive species, reactive chemical species. They react with halogens to give halides. They undergo hydrolysis to give hydroxides. They react with coke to give carbides. They show reactivity towards nitrogen to give respective nitrides. When they heated with sulfur gives sulfides. On combustion gives corresponding oxides. When react with acids produces dihydrogen, right? So yes, overall what we can say, lanthanides are also reactive species. They show reactivity towards various chemical species. You got it? Well, now coming to the uses of lanthanides. Okay, uses of lanthanides. So the first use, the best use of lanthanides is for the production of alloy steel for plates and pipes. So what is the major use of lanthanides? Means yes, lanthanides are widely used in the preparation of an alloys, particularly steel, that is in the preparation of plates and pipes. Then a well-known alloy is a mish metal. So what is a well-known alloy? Well-known alloy is a mish metal. What it contains, if I consider composition of this mish metal, the mish metal consists of around 95% metal, that is lanthanides, and around 5% iron, and traces small quantities of sulfur, carbon, calcium and aluminium. So what is mish metal? Mish metal is an alloy. Mish metal is an alloy of lanthanide with iron and traces of sulfur, carbon, that is coke we can say, calcium and aluminium. How much lanthanide is used here? Around 95%. Around 95% lanthanides, okay, and around 5% iron and trace quantity of sulfur, carbon, calcium and aluminum. All together constitutes a mish metal. So what is mish metal here? Mish metal is nothing but an alloy prepared by using 95%, around 95% of lanthanide metal and 5% of iron and traces of sulfur, carbon, calcium and aluminum. Okay, this is the well-known metal of a alloy of a lanthanides, right? Then if we consider the mixed oxides of lanthanides are employed as catalyst. Okay, the mixed oxides of lanthanides are employed as a catalyst in petroleum cracking. So what is this petroleum cracking means? It is a conversion of higher hydrocarbons into lower hydrocarbons, right? That is breakdown of an hydrocarbon, simply if you want to say. So mixed oxides of lanthanides are employed as catalyst in petroleum cracking, right? Well, then some individual lanthanide oxides are used as a phosphors in a television screen and similar to fluorescing surfaces. Okay, to develop color pattern in television screen, some individual lanthanide oxides are used. Then one more important concept here, if we consider lanthanides, what is the position here? They belong to third group and sixth period. Say lanthanides from lanthanum to lutetium, right? Similarly, if we consider actinium, they belong to third group, seventh period. Actinium, that is thorium to lawrencium. So here thorium, protactinium, uranium, neptunium, plutonium, americium, curium, berkelium, californium, einsteinium, fermium, metallium, as like elements are there. So after uranium, whatever the elements comes, they are called, that is neptunium to lawrencium, they are called transuranic elements. So is the one more important thing. So what are transuranic elements? The elements appearing after uranium. What are those? Neptunium to lawrencium, that is NP, neptunium to lawrencium, Lw. These elements are called transuranic elements. Okay, well. Now coming to the MCQs, the first one, what are the effects of lanthanide contraction? What are the effects of a lanthanide contraction? Yes, first one, decrease in the basic strength of lanthanide hydroxides. Yes, it is true. Then B is similar atomic ionic sizes of lanthanides. It is also true. Then post lanthanide effects, yes, it is also correct. Which means what is the answer here? All of the above is correct. So option D is correct here. So what are the effect of lanthanide contraction? Means because of lanthanide contraction, the consequences observed is there is a decrease in the basic strength of lanthanide hydroxides. There is a similarity in the atomic and ionic radii of lanthanides, and we are going to observe post lanthanide effect. Therefore, all of the above, all three options are correct itself. So option D is correct here, right? Well, the next one, which of the following is not a factor affecting basic strength? Which of the following is not a factor affecting the basic strength of hydroxides? Yes, we observe here number of H plus ions, atomic size, ionization potential, electropositivity. So what is the answer here? Number of H plus ions. Because we know basic strength depends on the atomic size. It depends on atomic size, it depends on ionization potential, and even it depends on the electropositivity, but it doesn't depend on the number of H plus ions, right? So it is not a factor, it is going to affect the basic strength. Okay, yes. Next one. Well, next one, basic strength is proportional to atomic size. So how it is related to atomic size? Option A, independent. Option B, directly. Option C, no relation. Option D, depends on atom to atom. Yes, it is directly proportional. So basic strength is directly proportional to atomic size, right? So larger the atomic size, what happens? It can readily donate data groups. So basic strength increases. Smaller the size, bond strength is more, so it donates with difficulty. Electrons are donated with difficulty, therefore basic strength decreases. So here basic strength is directly proportional to atomic size. Yes, the next one. Which of the following hydroxide is most basic? Yes, in the last session itself I have mentioned that. So what we said, from lanthanum to lutetium. Lanthanum to lutetium. What happens to the size? Atomic size decreases. Atomic size decreases because of lanthanide contraction, size decreases. Now if you consider basic strength depends on what? Basic strength depends on the size, right? Basic strength depends, is directly proportional to atomic size. Both are directly proportional, means if size is more, basic strength is more. If size is less, basic strength is less. So hydroxide, say lanthanum hydroxide, LaOH taken twice, lutetium hydroxide, LuOH taken twice. Means if you compare the basic strength, here lanthanum size is large, lutetium size is less. Okay, as size decreases, basic strength also decreases. So what they are asking, which of the following hydroxide is most basic? Means the one having larger size will be the most basic. First we look for the options. Cerium hydroxide, okay, praseodymium hydroxide, lanthanum hydroxide and lutetium hydroxide. Which one is more basic? Lanthanum hydroxide is most basic. What is the least basic means? It is the lutetium hydroxide. Okay, well, next one, which of the following are not chemical twins? Which of the following is not a chemical twins? So hafnium and zirconium and hafnium, they are chemical twins, right? Because of lanthanide contraction, there is a similarity in the atomic and ionic radii of hafnium and zirconium, so they are considered as a chemical twins. Next one, neodymium and talcum, yes, they are also chemical twins. Second is option is also correct. They are asking which of the following are not chemical twins. They are chemical twins. Then these are not answers. Then tungsten and molybdenum. Yes, they are also chemical twins. Then what is the last option? Scandium and titanium. They are not a chemical twins. So what is the question here? Which of the following are not chemical twins? Means this scandium and titanium are not chemical twins. So what is the answer here? Option D. Well, so with this I am going to conclude about this session. Again in the next session we go for other concept. Okay, thank you, be safe.